Okay, so our next speaker is Fahad. Fahad is a fourth year biomedical biology student at Laurentian University. His research focuses on occupational biomechanics and vibration exposure as well, with an emphasis on foot transmitted vibration and protective footwear. He is interested in applying biomedical research to improve worker safety and evidence-based equipment design. And so today we have Fahad presentations called From the Ground Up: How Work Boots Affect Vibration Exposure.
Hello, everyone. Good afternoon. My name is Fahad, as already mentioned. Today, I'm going to be presenting on evaluating the effectiveness on work boots in reducing foot transmitted vibration using an instrumented insole. Um, my supervisors are Dr. Brent Levers and Dr. Katie Goggins. Dr. Katie Goggins, thank you very much. And my thesis is completed in accordance with the requirements of the School of Natural Sciences here at Laurentian University. So just to give you guys a bit of an idea and a bit of preamble of what we're going to be going over this afternoon. Going to start off with a bit of an introduction to occupational vibration exposure, give you guys an idea of what that looks like. Then I'm going to give you guys an idea of what the current gaps in literature are like, my objectives for my thesis, and then a methodological summary of what I actually did during my experimentation, some results that I have so far, some concluding thoughts, and then my references. All right, so just to jump right in, to set the stage a little bit. Most occupational vibration research falls into two main categories. Whole body vibration, which is vibration transmitted through seats or standing surfaces, found in things like heavy equipment. It has very defined exposure limits and are very well defined and regulated under ISO, or the International Standards Organization, specifically Standard 26311-1. After that comes hand-arm vibration. Now, that is experienced via things like grinders or jackhammers. It is also very well studied and it has extremely clear exposure limits as well, defined by ISO as well. The standards are 5349 and then 10819. Um, but these focus specifically on attenuation requirements and specifically limits. Now, my research focuses on foot transmitted vibration, and that is a bit of a gap. Foot transmitted vibration is essentially vibration that enters through the body from the feet while standing. Workers experience this usually on vibrating platforms or machinery. Compared to hand-arm vibration, there's actually currently no ISO standards in any capacity that evaluates footwear based on vibration attenuation. Before we jump further into that, I'm going to give you guys a bit of an idea of what the pathophysiological standpoint looks like for foot transmitted vibration. Now, vibration entering to the feet is benign on most cases, but in a chronic standpoint, when it comes to the exposure after a long period of time, the first set of symptoms that most people actually experience is numbness, tingling, and a loss of sensation. And this is due to nerve damage. The repeated stimulation of these nerve fibers after multiple experiences with chronic vibration leads to minor but present numbness, tingling, and loss of sensation. After that, individuals will experience vasoconstriction. Now, vasoconstriction is defined as the narrowing of blood vessels within the extremities, and this will lead to reduced blood flow, increased blood pressure, and can cause things and conditions such as vibration-induced whitefoot. After that, we have muscle fatigue or pain. Now, that repeated stimulation over time can also lead to microtrauma in the muscles. And this can lead to reduced muscular endurance and affecting balance, causing problems with gait. In terms of the scale of the problem, foot transmitted vibration, just occupational vibration exposure in general, affects millions of workers globally, with around 4 million workers exposed just in the US and a cost of around 45 to $54 billion. It's a pretty big problem, but just very quiet in the way it does it. There's also, when I mentioned earlier, I mentioned that there was some pretty massive gaps in safety standards. Gloves, as I mentioned earlier, have very specific standards for testing and attenuation. Boots, on the other hand, have no such standard for vibration attenuation in any capacity, with the current standard, the CSA Z195, focusing specifically on toe and slip protection, but nothing on reduction. There's also some research gaps. When it comes to the current literature, most past studies have examined barefoot conditions or very controlled postures that work, but doesn't reflect actual real-world environments. When individuals and workers stand on platforms, they're not standing in perfectly fixed positions. They're actually standing maybe more freely. One of their feet are out. It's more natural. And to our knowledge, no studies have measured foot transmitted vibration through real safety boots in situ, which makes this a very novel study within the field. So that jumps into my hypothesis and my objectives. The main goal of my study is to quantify how different safety boots influence vibration, transmissibility, and this is all done across very relevant frequencies within the body. I'll get into that a bit more later. But we also wanted to see whether subjective discomfort aligned in any meaningful way with measured vibration. The way we did this, we recruited 10 healthy adults from Laurentian University, and participants were screened to include recent injuries, neurological conditions, or anything that would confound vibration responses, essentially make the conditions worse. My experimental timeline looked pretty much like this. The first thing we would do is we would begin with a pre-test screening utilizing a tinnitus scale to record each participant's information and body composition. We After that, we would instrument them, and we would mount the way we do this by mounting sensors and accelerometers, and we would also utilize the instrumented insole or that I mentioned earlier. I'll get into this a bit more further. After that, we exposed them to specific amounts of vibration. The participants would stand on our rotopod for a series of trials, and after that, they would complete a post-exposure survey. The survey would allow us to kind of gauge their discomfort based on the boots and the actual profiles that they were experiencing. So we start with pre-test screening. We then instrument them utilizing accelerometers and sensors, instrumented insole as well, and then we expose them to our vibration. And lastly, we jump into some post-exposure survey questions. The boots we utilized for my experiment were four. We utilized an Oliver in Porin, a Terra 8 Gantry in metal, and then a copper thermic green and an Oliver. And then we also had barefoot as a control. But the reason we utilized these four was because they represented a range of real-world designs and materials. This variety allows us to test whether softer materials or maybe heavier materials were more and maybe some more protective designs are better at reducing attenuation, just giving us a bit of an idea of what specifically, or giving us idea of what ranges of boots would be best for attenuation. And then obviously barefoot control to give us an idea of what it naturally looks like. After that, this is our Rotopod 3000. This is a vibration platform. So it's essentially 6 degrees of freedom, and it's a vibration simulator replacing real world flow transmitted vibration. So 6 degrees of freedom essentially means it's 3 degrees of translation. So your usual X, Y, and Z. It also has some rotational translation as well, or rotational, and that's where the other three come from. So it's 3 in terms of translation and then 3 in terms of rotation, 6 in total. Now, we used 3 vibration profiles, low, medium, and high risk, and this is based on real field data from industrial and mining machinery. The definition low, medium, and high is not inherently what we exposed them to, but after an 8-hour period, if they were exposed to this continuously, it would be low, medium, and high risk. But within our 40-second exposure period, it would not be low, medium, or high risk. Yeah, and then, yeah, so 40 seconds, just exposing them, and then we give them some rest period in the form of 10 seconds. And this was all done in a randomized order, just so we made sure it was extremely accurate. Jumping on to what our transmissibility measurements are, because we're talking about transmissibility here, right? We're talking about attenuating transmissibility. Transmissibility essentially represents how much vibration is transmitted from the vibration source, so in this case, the platform, to a measurement site. And this could be any anatomical site. We're going to be focusing mainly on the heel and toe, but it could be any anatomical site because we did have instrumented insoles in different parts of the body. It is a calculated ratio of acceleration measured at the body site to acceleration measured at the platform in this case. In simple terms, a transmissibility value of 1 means the vibration is unchanged, right? It means that the acceleration at the site and the acceleration at the platform are identical, meaning that there was no actual attenuation or any amplification. Values below 1 indicate attenuation. That's actually what we want when we're testing these boots. And values above 1 indicate amplification. We don't want that. And the transmissibility was calculated in the frequency domain. And this allows us to examine how vibration transmission varies across frequencies rather than collapsing everything into a single value. I'll get more into that a bit more later, but This is important because footwear does not behave the same way at all frequencies, and amplification can occur even when overall vibration magnitude decreases over time. Now, our experimental setup, I'm gonna kind of spend a bit of time on this. We had accelerometers placed at the head. This is to measure our C7 vertebrae, so or the cervical spine. And then we had an accelerometer placed here at the tibial tuberosity, right below the knee. And then we had our main accelerometers at the instrumented insole, and this was placed at the heel, and then, oh, sorry, at the heel and also at the toes. And then we also had an accelerometer placed at the actual platform right over there, and that was just to measure as a baseline, right? That's our reference point. The sensors would record vertical and horizontal vibration transmission through the kinetic chain. We are focusing on vertical transmission in this case because that's more relevant to standing vibration, but we do have X and Y in the form of horizontal vibration for more in-depth analysis when we get into that much further. Now, in terms of our participant data, we had our 10 healthy adults, six of them were male, and then four of them were female. They aged for the range with their ages was 20 to 25, and their heights on average was 1.77 meters or 5'10 for males, and then 1.64 meters or 5'4 for females. Their average body masses were recorded at 85 kilograms or 190 pounds, and then the males were 61.5 kilograms or 135 pounds, or the females. Now, further into our results, I'm going to be comparing our two graphs here. We have a graph that represents insole heel, the heel transmissibility in the z-axis, and this is different profiles. So when you look at this graph in specific, you're going to notice that the x-axis has our frequency hertz, and the y-axis has our transmissibility, and then we have a black line here. That's our reference point. So remember when I mentioned that a ratio of 1 indicates nothing happens? So if anything goes above this, it's amplification, and anything goes below this, it's attenuation. That's what we want. So we want pretty much every single value to be below, but obviously sometimes you have amplification. Now, what's it called? We also have it in three different profiles. So we're going to be starting in our low profile. Now, you might be asking why we're using the heel and toe, even though we have accelerometers at the tibial tuberosity and the head. The reason we're using the heel and toe specifically is because the heel is the primary load-bearing contact point during standing, and is often where vibration enters the body most directly. In contrast, the toe region represents a more compliant interface and may behave differently in terms of dampening. Now, in terms of comparing the two regions, we can start to understand not just how vibration is attenuated, but how vibration is redistributed across the foot, right? Instead of just focusing on how it comes in, it's distributed entirely through the foot. Now, in the low risk profile, while both figures showed that increased frequencies will observed. So you'll see that as we increase in frequency, we're technically always we're going down in vibration, and this is very much easily more observed in the toes, but in the heels, it is also somewhat observable. Um, so increased frequencies kind of tell us that we get better attenuation. The heel shows more variability because we'll see sometimes it is amplified even in these regions. But the toe, on the other hand, is extremely straightforward. The reason for this is because there's a resonant frequency. Now, Kaylee previously mentioned the concept of resonant frequencies. Now, resonant frequencies are ranges or biological frequency ranges within the body where there is essentially a positive amplification due to the frequency that is being transmitted and the frequency within the body matching. So it's constructive feedback. This will lead to increased vibration and increased movement, and this can actually cause more damage and a little bit more fatigue. It amplifies the negative effects that I mentioned earlier with FTV. Here we see some amplification around the resonant frequency of the heel, which is around 15 to 36 here. So we see a bit more amplification here, but the barefoot control sees more attenuation compared to the boots. This tells us that the materials utilized in the boots have a tendency of amplifying the vibration within these regions compared to those that we see within the toes. So the materials within the toe see a little bit, and materials within the toe may see more attenuation versus the materials within the heel seeing more amplification within these regions, and this is very important. Another reason why you may see a much more straightforward trend is because the resonant frequency of the toe is very much higher than the resonant frequency of our heel, and it's actually outside of our frequency range. That is another pretty important reasoning for this trend here. Moving on to our medium risk. So this is the risk that's a little bit greater than low, but slightly less than our high one. You will see our reference range is also here as well. So we have references ranges in all of our graphs, and you'll see some minor peaks within our boot two, and then you'll see our control and our other boots here, but generally similar trend is observed in the low profile. Similar ranges, and this is for the heel and the toe. Now, this profile represents a balance between signal clarity and real-world relevance without excessive variability, seen at very low loads. We do see a bit of a clearer picture, but still generally very variable between all the boots, right? It's very hard to tell which one is the best within these graphs. Lastly, at our high profile, you can observe a similar trend as well. As frequency increases, we see a little bit more attenuation, but there's still inter boot and inter control variability. As we said already, the toe is also much more clearer downwards. It will, as the frequency increases, there is much greater attenuation. Now, in terms of some overarching thoughts, when we look across all three profiles together, a few consistent patterns emerge. First, foot transmitted vibration is strongly frequency, load, and location dependent. The frequency, as I already mentioned, as we increase in frequency, there is a little bit more of a downward trend until we reach a resonant frequency for our heel. In terms of load, it's essentially dependent on the fact that, and load and location, it means that the heel, because it's the most direct point of contact for transmission, you'll see very different ways of transmission and attenuation versus the toe, which is a location that isn't more direct, it's more outside of that. Secondly, boot performance is not uniform across the foot. The heel is more prone to mid-frequency amplification, while toe shows more consistent attenuation. Third, higher vibration levels result in more stable and interpretable transmission patterns, which is important for future testing and standardization. I also wanted to mention our discomfort ratings and our self-reported discomfort ratings that I mentioned earlier. Because exposures were short and within safety limits, discomfort remained low across all conditions. This created a floor effect, which limited our ability to detect differences between boots. Importantly, this suggests that changes in transmissibility occurred without inducing discomfort under these controlled conditions. Moderate or greater discomfort was rare and participant specific, with about 6.5% being mild and 3.3 being moderate. No severe discomfort was reported. In our self-reported discomfort, 0 meant no ache or pain. 1 meant mild discomfort. 2 meant moderate discomfort. 3 meant severe discomfort, and 4 meant very severe discomfort. We never saw ratings above 2, meaning that no one ever experienced severe or very severe discomfort. That is actually very positive and means that we can reduce transmissibility of vibration without causing discomfort. That is extremely important. On top of that, there was actually no statistically meaningful differences in discomfort between each of the boots, meaning that no specific boot was more discomforting than the other. Now, at this stage, it is important to note that while trends are clear, the current sample size does not support definitive ranking of boots. Inter-individual variability remains high, and some boots perform better at certain frequencies but worse at others. This reinforces the need for statistical analysis and larger sample sizes before making executive decisions about footwear performance. So, some concluding thoughts. This study represents the first in situ evaluation of foot transmitted vibration using instrumented insoles. It provides some pretty quantitative data that's currently missing from footwear safety standards, and it has the potential implications for manufacturers, industry decision makers, and future CSA and ISO updates. This is a novel study that has some true impact in the future. Now, here's some references for those of you who would like this for your own information. Thank you for listening, and I'd be happy to answer any questions now.